All right, chapter 7, part 2. We're going to continue the part we talked about different features on Earth. We're going to continue that. So let's see. So we have some sort of a radiation protection on Earth. We all know that, right? Because of the atmosphere. Atmosphere blocks some of the lights that is coming from the sun, and it only lets almost 100% of the visible light to go through. Some sort of a UV light will be absorbed in the top of the atmosphere, and almost everything in regards of X-ray will be absorbed in the top of the atmosphere. So all X-ray light is absorbed very high in the atmosphere. Ultraviolet light is absorbed by the ozone, O3. Now, we have a protection of an ozone layer, as all of us know, right? But what other implication does this ozone protection layer has? So obviously we have no free oxygen in the atmosphere. So if we didn't have no free, it's better to say it this way. If we did not have free oxygen in the atmosphere, we did not have ozone layer, so no UV protection. In other words, what's happening is if I had, let's see, okay, if we didn't have an extra O on the atmosphere, this could not have a reaction with O2, okay, to create ozone O3. The fact that we have so many CO, we produce so many CO and CO2 in the atmosphere, when we're talking about that we're producing greenhouse effects and we're causing the global warming, is because of this. So if you have, where am I? Okay. If we have, this is really hard to adjust at some point. Doing this. Okay. So if you're creating CO, which we do all the time, this CO and this extra O will do a reaction to create CO2. Okay? Kind of like that. So the fact that we are producing a lot of carbon monoxide, okay, CO, and that will do a reaction with the oxygen, the atomic oxygen, rather than creating ozone, it'll create CO2. And the CO2 is one of the greenhouse gases. Okay. Now, that means rather than creating a ozone, the ozone is not being created, and then there will be a hole in the atmosphere. So an average data from 4 years of 1970s show no ozone hole, but an average data from 4 years in 1990s. And we were talking about 1990s, we were talking about 30 years ago, show the rapid development of the ozone hole, okay? Greenhouse effect. The greenhouse effect, we're gonna talk about it extensively here in part 2 and part 3. So what's happening is this. We have a visible light path through our atmosphere, coming all the way from top to bottom. So these are, the density of the molecules are much higher when close to the surface of the Earth. As we go up, the density will decrease. Now, some of these visible light will be reflected from the Earth's surface, right? But then some of them will be absorbed by the Earth's surface. Once the visible light gets absorbed by the Earth's atmosphere, it will heat up. The Earth's surface will heat up. It will do some thermal radiation in an infrared wavelength, which are these red arrows. These thermal radiations in infrared wavelengths will be absorbed by these molecules and these atoms in the Earth's atmosphere. They'll absorb it, they'll pass it to another molecule, pass it to another molecule, so on and so forth. So you end up with a very warm atmosphere, okay? Now, there are certain molecules and atoms who do that, actually absorb them. Not everything can, like for example, nitrogen molecule N2 doesn't do anything. Oxygen, O2, symmetric hydrocarbons, other than methane, don't do anything. They don't absorb the infrared. But a lot of the greenhouse that we're producing will actually cause these effects. So let's see how some gases warm the Earth. So if you're looking at this, this is the exact same thing that I was talking about. Invisible light is coming in. Some clouds were reflecting them. It will reflect from the surface as well. But then some of it will be absorbed by Earth surface. It will be reflected in the infrared radiation. It will be absorbed by carbon dioxide, methane, water, and then so it'll just pass to other molecules. So greenhouse gases are water. They are, they are CH4, and they are CO2. So these three, CH4, CO2, and water, are the most most effective greenhouse gases. Okay. So if we have too much of a greenhouse gas, temperature will get really, really high. This is exactly what's happening in Venus. Remember, we talked about Venus when we were giving the introduction to the solar system. Venus, the temperature between day and night does not change much. It's always around 450 degrees, and it's really high. It's because of the unbelievable greenhouse effects that's happening in Venus. All right. So if you're looking at Earth's atmosphere, as I said, it absorbs lights based on its wavelength. So almost all the visible light coming through to the bottom of the Earth's atmosphere on the surface. If you want to observe, if you want to, do some observation, stars, galaxies, and etc., we build our telescopes right on the top of mountains. We're about like 4 kilometers high, right? Like right here, 4 or 5 kilometers high, like the mountains Hawaii, Mauna Kea in Hawaii, right? In order to get, near infrared to infrared wavelength. If you want to go exactly to the infrared, you have to have a telescope like SOFIA, which is in the Boeing 747, and you have to climb up to like 10 kilometers high. On the other hand, radio wavelengths will get all the way through, and without any problem pass through the atmosphere. X-ray, gamma ray will be absorbed on top of the atmosphere, somewhere about 30 to 40 kilometers above. When we're seeing some of the perfect images, visible images from the universe, they always say it's coming from Hubble telescope. It's because Hubble is working in the range of visible. So just have that in mind as well. All right, greenhouse effect. Certain molecules let sunlight through, but absorb escaping infrared photons, which is water, CO2, and CH4, methane. So symmetric molecules like O2, N2, these are not greenhouse gases. Let me show you this video. I'm gonna stop sharing, and then I am going to share screen. I hope I'm not making a mistake this time. So this should do it. Here we go. So, so what you can see here is that these are the incoming light from the sun coming to the surface. If we had no atmosphere, this will get to the surface and being reflected from the surface. Like at the atmosphere, we can see some of these will be absorbed. Some of them will go away eventually, right? But some of them will be absorbed and then pass to the next molecule, coming back to the surface. So this is causing the surface or the atmosphere to heat up. Okay, Going back to our PowerPoint. There we go. Moving on. Greenhouse effects. Is it really that bad though? Because of the greenhouse effect is Earth is much, look at this, much warmer than it would be without an atmosphere. But so is Venus. Okay, so it's a perfect amount of greenhouse that we need on Earth. If it's too much, global warming will happen. We'll be in trouble. If it's very low, we're not going to be a warm atmosphere, so we're not going to have liquid water, or we're not going to the conditions will not be suitable for the life to happen on Earth. So we have to have a right amount of a greenhouse, gases on the atmosphere. Thought question. And we're going to get to this later on as well, but why the sky is blue? I think we talked about it before. A, the sky reflects light from the ocean. B, oxygen atoms are blue. What? C, nitrogen atoms are blue. No way. They don't have a color. Anyway, D, air molecules scatter blue light more than red light. E, air molecules absorb red light. The answer is D. Air molecules scatter blue light more than red light. Let's take a look at this. Okay, so if you're at noon, let's say that we are in Hawaii, okay, in Hawaii, around like noon, 12 o'clock at noon, you can see that the sun is directly above you, right? So you can see everything being, completely blue. The reason it's blue is because the atmosphere scattered blue light from the sun, making it appear that everything is blue above you. So it's being scattered everywhere. But when it's very close to the horizon, when it's very close to the sunset, which is like probably in Florida at that time, right? So even though the blue light being scattered, you're looking directly at the sun, and the sunlight will go through the atmosphere, which is now much thicker. So let me explain what I mean. If I am looking at Earth kind of like that, if this is Earth and this is you, okay, and if this is atmosphere above you, all right, so if you're looking at an object, if you're looking directly overhead, take into account this much of an atmosphere. But if you're looking that way, you're taking into account this much of the atmosphere, okay? Which is exactly what's happening around sunset. So that's why sunset or sunrise pass through the sun will pass through the atmosphere to reach to you. But most blue light is scattered away, leaving a red light that gives the sky to a reddish color. Right, I think I can clean that. Perfect. Okay, what have we learned? Why is Earth geologically active? Earth retain plenty of internal heat because it is large for a terrestrial planet. Remember this relation? You remember this relation from part 1 that we had 3 over R. The surface to the air, the surface area to the volume ratio is 3 to the R. So since R is really high for Earth, it's bigger. This whole factor is less. It means it will keep its internal heat. Okay. Now, now that heat drives geological activity, keeping the core molten and driving geological activity. The circulation of a molten metal in the core generates Earth magnetic field. Remember, in order to keep our atmosphere, we need to have some sort of a protection from the solar wind that doesn't, to keep the atmosphere safe. Otherwise, the solar wind will blow our atmosphere away. All right. What geological processes shape Earth's surface? Impact craters, craterings, volcanoes, tectonics, erosions by wind, water, ice, and so on. How does Earth's atmosphere affect the planet? Erosions, protection from radiation, and greenhouse effect. Now, let's go to part 7.2, Mercury and the Moon, geologically dead. So our goals of learning for this particular part is why there are geological activity on the Moon. Was there a geological activity on the Moon or Mercury? Do they have a past activity? And if so, how do we know that? So they look really the same when you're looking at them, even though Moon is a little bit smaller than Mercury, but their surface is dead. They don't have any activity. They've been the same for thousands and thousands and millions of years. When we're looking at the past of the Moon, we see that there are some volcanic activities about 3 billion years ago. Remember, the Moon is pretty much as old as Earth. It's about 4.5 billion years old, as old as solar system. And there are some volcanic activities shows like that they came and filled this crater with lava, and then now we call it Maria. Remember a week before the spring break when I show you the past history of the Moon? By the way, that web page is still in the Blackboard, so go ahead and watch it. The Moon is now geologically dead. Nothing is happening in the Moon anymore. Mercury. Mercury has a mixture of heavily cratered and smooth regions like Moon. And those smooth regions are likely ancient lava flows. So these smooth regions are probably just lava flows. Okay? Tectonics and Mercury's. There are long cliffs indicating that Mercury shrank early in the history. And if you see these lines going across, it means that it has shrank before. So it was a little bit bigger, but then the surface and these craters move, and this long cliff indicate that the Mercury had a history of history just like what we had on Moon. Recent geology on the Mercury. So these lighter areas, what you see here, the blue color or white color, are thought to be halos formed as easily vaporized minerals escape. If there are a lot of information that I want to talk about, especially about Mercury, but I'm just in a debate with myself of how far I want to go. So I have this Johns Hopkins University Applied Physics Lab webpage right here. The mission that got a lot of information about Mercury was Messenger. So go ahead to this webpage and you'll find a lot of more information if you're interested. What have we learned? Was there ever geological activity on Moon and Mercury? Early craterings on the Moon and Mercury is still present. We can see them. Now it's dead, but we could see the past when we were looking at the present time, indicating that activity ceased long ago, about 3 billion years ago. Lunar Maria resulted from early volcanism, and tectonic features on Mercury indicate early shrinkage. 7.3, it's another subchapter talking about Mars extensively here. A victim of planetary freeze drying. Our goal of learning is what geological features tell us that water once flowed on Mars, and why did Mars change? Okay, Mars versus Earth. Very interesting topic. When I was talking about Mars, this image came to my mind, so I was like, I'm going to put this here. Martians probably look like this. I don't know, but we definitely look like that on Earth. So just giving you an idea to compare Mars and Earth, we know that Mars is very smaller than Earth. 50% Earth radius. It's 10% of Earth mass. It's further away. It's in the edge of the habitable zone. And that's what we call it. It's about 1.5 AU from the sun. The axis tilt is pretty much the same as Earth. Remember, the axis tilt of the Earth was, what was it? 23.5? 23.5 degrees. Sorry for my handwriting. And then it has a thin CO2 atmosphere, so it got a little bit of a greenhouse effect. But the main difference is that Mars is way smaller, half size of the Earth. Okay, here we go. So even though it's smaller, sometimes happier. Martian atmosphere. So as I said, it's mostly CO2, okay, 95% of it's CO2. There are some nitrogen molecule, hydrogen, helium, and some water, but it's mostly about 95% of the atmosphere is CO2. Now, the question that it brings is that if it has 95% CO2, if it has this much of CO2 in its atmosphere, and we know that CO2 is one of the greenhouse gases, why it is not warm? Why temperature is not high? It has this many of the Earth CO2, it should be really warm, just like Venus, right? But it's not. The reason is, even though it has 95% CO2, the pressure is not really that much. So it has 95% of the atmosphere is CO2, but the atmosphere itself is not really that much. Okay, it's about over 1/50th, 150 Earth atmosphere's pressure. Okay, so I hope you understand what I'm just talking about. 95% of its atmosphere is CO2, but the atmosphere itself is not really that much compared to Earth. So it doesn't get a lot of greenhouse effects. Why is it red? Okay, the rock is reddish due to iron oxide, or the rust, okay? So what's happening is that where the UV sunlight breaks down the water, releases the O and hydrogen atoms, so H2 plus O, and that extra O react with Fe, which is just iron, right? So that means that now you have iron oxidized, okay? No ozone layer to protect it from UV. So that's why the UV light will come in, break down the water, releasing the oxygen atom plus hydrogen atom. And then that oxygen and that Fe, so I have kind of looking like that. So I have Fe plus oxygen giving me iron oxide. Okay, so, and that means it's rusty, it's reddish. All right, so let me see how I can clear this. And by the way, you might see my cursor moving all the way up to this top panel, but you can't see the panel. So if you see that I'm moving my cursor, it doesn't mean that I'm crazy. I'm just I'm just playing with this panel up here. Okay, seasonal effect on Mars. As we know, it has an axis tilt just like Earth, 23.5 degrees, but since it has a very high ecliptic orbit compared to Earth, it got a very high extreme southern hemisphere seasons. So if you're looking at the Earth orbit, it's pretty close to a full circle, but if you're looking at the Mars orbit, it's actually very elliptical. So you can't say it's a perfect circle just by looking at it, because the eccentricity is higher compared to the Earth orbit. So what it means that even though it's only about 23 degrees tilted, since its elliptical orbit has much higher eccentricity, it has more extreme seasons, especially in the southern hemisphere. It also got a lot of dust storms. These are the two images of the Mars in 2001. So June 26, 2001 and September 4th, 2001, you can see that it got a lot of dust storms. In order to, if you're interested to know more, go to the Goddard website, NASA Goddard. You have it right down here. You can find a lot more about Mars and seasonal winds, things like that on Mars. So when we're looking at these geological features, they can tell us a history. They can tell us what it looks like in the past. Remember, I was speaking about the same thing, the first session of the class. When we're looking at the most distant light in the universe, we're looking about 14 to 15 billion years ago. So when you're looking at the light coming from something, you're looking at in the past. You're looking at now, but you're looking at as it was in the past. So when we're looking at the Mars surface, we can know a lot about its history. We can know a lot about its past. These are just some of the riverbeds. Some of the, it indicates, especially the way it looks like the rivers on Earth, right? But there's obviously no water. So the water should have gone somewhere, which we're gonna find out where it went and why that happened. So we have some eroded craters. So these craters have been eroded. The conditions in the craters indicate some surface history on Mars. Remember, since Mars has a very thin and not very dense atmosphere, we can see its surface pretty clearly. This is an overall map of the Mars. There are two very well-known, geological features. The first one is right here. It's a mountain, Olympus, which is a volcanic mountain right down here. And the most recent volcanics that we have is about 180 million years ago on the surface of the Mars. It is the biggest volcanoes in the whole entire solar system. Even though Mars is really small, it has the biggest volcanic mountain. And the second one is this, the Great Canyon on Mars. The Great Canyon of all time is actually not on Earth, it's on Mars. And we're looking at, if you go to some details about these two features, you can fit the whole state, the Arizona state, in this volcanic mountain or Olympus. It's, as I said, the biggest volcano in the solar system. It's about 700 kilometers in diameter, 25 kilometers high. Just to give you an idea, to compare, the Mount Everest, which is the highest mountain on Earth, is about 8.8 kilometers high. This one is 25 kilometers. So it's really big. The other one is this canyon that I was talking about. It's big enough. This canyon formed, long ago, and it's 4,000 kilometers, 2,500 miles long, 6 kilometers deep, and 200 kilometers across. Technically, you can, fit, it can run across the entire, United States, all the way from New York and Florida, all the way to California. If you're interested to know more, I was just looking at a video about this. I put the link down here. It's on YouTube. Go ahead and watch it. We're not going to do it right now. It's a lengthy video, but I'm just having this link here. Go ahead and watch it at your convenience. Okay, Moving on, in 2004, Opportunity rover provided strong evidence. So we sent rovers, or we sent spacecrafts to study, Mars and all the planets so far. So the Opportunity landed on Mars in 2004 and sent us this picture. It really looked like what we have on Earth, right? And it can tell us that the Mars was warmer in the past, and then it suddenly cooled off. So these pebbles that discovered by Curiosity rover, as I said, we sent so many spacecraft and so many rovers to this planet because we were really interested to know why it lost all of its features. It found some similar features that we saw on Earth. Here, the Curiosity find these layered rocks, indicating that there has to be some sort of a history of water or lakes in the past on the surface of the Mars, which is exactly what we see on Earth. But today, since it's all dry, all of its water are trapped underground. So all of these blue features that you see, or the kind of whitish, bluish areas that you see, these are all trapped water, icy waters. Now, you might have asked this question, but why did Mars change? What happened that caused this beautiful planet to change so drastically over millions of years? So, climate change on Mars. Let's take a look at that. So Mars has not had widespread surface water for 3 billion years. The greenhouse effects probably kept the surface warmer before. Now, somehow Mars lost most of its atmosphere. The reason is it cooled down, okay? Once something is cooling down, the core temperature is cooling down. So it's not generating geological activities. Once the geological activity is not being created, and the core is cooling down, it is causing the magnetic field that you see here to slow down and disappear over time. If the magnetic field is disappearing over time, the solar wind that will cause the atmosphere to go away. So that's why we think that Mars had a thicker atmosphere in the past, heavier, it was warm enough that they had a liquid water, but right now it doesn't because it lost its magnetic field. Okay, so in the past, warmer core generated stronger magnetic field, okay, and then warmer interior caused extensive volcanism and outgassing. Okay, thicker atmosphere created warmer and possibly wetter climates. Now and then, a stronger magnetosphere protect atmospheres from a solar wind. So it was pretty much looking like Earth before. But Mars today, first, lack of a core convection means that no global magnetic field. Wind will come, solar wind will come and destroy the atmosphere. Cooler interior no longer drives extensive volcanism and outgassing. So it means it doesn't have this thick, warm atmosphere around it anymore. Okay, now some remaining gases condense and react with the surface at the north and south pole. And then thinner atmosphere reduce the greenhouse effects. Even though it has CO2, which is one of the greenhouse gases, it now has a less dense atmosphere, so the greenhouse effect is not really that much of an effect. Let's take a look at this. What protects Earth's atmosphere? Think about it. First one was magnetic field. Second one was greenhouse effects. Okay, so Mars lost its magnetic field, which is one. right here, magnetic field, and never had, water, or never had water in its atmosphere, or the greenhouses. It had a lot of nitrogen, it had a lot of CO2, but it did not have oxygen or O2 to create O3 and ozone to protect its atmosphere from UV light. So if you want to answer this, the first one is the magnetic field, second one is greenhouses plus O3, which is ozone. Okay, so there is this MAVEN spacecraft measuring the loss of the Mars atmosphere today. We're looking at these oxygen and hydrogen and carbon going all the way, from even still today, it is happening. It's going away from, Mars atmosphere. Let's take a look at what we have learned. What geological features tell us that water once flowed on Mars? Dry riverbeds, eroded craters, floodplains. When you're looking at the surface of the Mars, it really indicates that it has a past history with a lot of water in it. Mars today has ice, underground water ice, and perhaps pockets of underground liquid water. We don't know yet. That's why we use perhaps here. We're like 90% sure, but we have a long, we have a long way to go to be sure about this. Why did Mars change? Mars' atmosphere must have, once been much thicker, so its greenhouse effects to allow liquid water on the surface, just like what we have on Earth. And then somehow Mars lost most of its atmosphere, perhaps because of the declining magnetic field. So that was the end of part 2. We're going to continue with part 3.